Hi everybody, welcome to lecture. I'm going to keep talking about angular momentum. Excuse me. Uh, Angular momentum, L vector. And we have spent some time already talking about the angular momentum for a point mass as it was moving linearly and as it was moving in circular motion for the conical pendulum problem. And for the point mass, I've written up the equation here that the angular momentum is r crossed with the linear momentum m times v. But now we want to talk a little bit about angular momentum for a rotating rigid body. So angular momentum vector for rotating rigid bodies. And you can see here that very analogous to P equals to m times v. We find the angular momentum, the rotational mass times the rotational velocity. So it is kind of like m times v, just for the rotating rigid body. So here again, I is moment of inertia, and this is angular velocity. And a real quick proof helps us to understand the form of this, besides just taking it for granted. So let's say I have a rigid body that's rotating. And here is the axis of rotation that it's rotating about. Perhaps it's moving with some omega circling around. And this rotating rigid body is made of a bunch of different point masses that are fixed in place relative to one another. That's what makes it rigid. And for every individual point mass, associated with them is a linear momentum. So as this rotates around, they all have kind of a tangential velocity depending on their position, on the body. It'll be bigger and smaller or pointing different directions. But it is important to note that all of them, all of them will have an r vector. So this green arrow is their r vector, and this would be their tangential velocity, and it's directly related to m times v vector, which is just their linear momentum. And so I may not have drawn this too great, but each one of these has a different r vector, a different tangential velocity, but they're always perpendicular with respect to one another. And that tangential velocity really does represent the linear momentum of the system. So if I wanted to find the total angular momentum of a system like that, all I would have to do is to sum up the individual angular momentum of each point particle fixed here in the rigid body. And what that would look like would be the sum over r sub I crossed with m v sub I, this again being the angular momentum for a single point particle. All of the r sub I are different, all of the v sub I are different, but if you remember, what is not different is omega. And, the absolute value of the angular velocity omega, remember, is a uniform quantity. And what I'm going to try to do is to get this formula in terms of omega. So for now, I'm going to assume that this is the positive y hat direction. And although it may not look like it, this rotating rigid body is kind of in the zx plane. Okay, so this is a three-dimensional drawing, believe it or not. Body's in the xz plane, and the positive y hat direction indicates the direction of omega. And so if I thought about some kind of point particle, maybe one here, its r vector crossed with its mv vector, like I said, all of them are going to be exactly perpendicular, and the cross product, if you line your pinkies up with the first vector in such a way you can fold it into mv, what you'll see is that the resultant vector r cross mv will point in the positive y hat direction. So for every single one of these, they point in the positive y hat direction. For all of them, and for every single one of them, r is perpendicular to mv. So this would be like RMV sub I sine of 90 degrees, which is 1. And so this sum really just becomes, and I'm going to pull that positive y hat out of there because it's a constant, r sub I, m sub I, v sub I, all in the positive y hat. And so this is where I'm going to use this idea that omega is uniform for the rotating rigid body. And if you remember, omega is equal to v sub I divided by r sub I. And so the numerator and the denominator can be different for every single point particle, but their ratio is the same. So what I'm going to do is to replace v sub I with omega times r sub I in this sum. Where omega does not get a little sub I because it's uniform and a constant. And I'm going to go ahead and pull it out of the sum. And what I'm left with, you can see, is actually the omega vector. So omega points in the positive y hat direction along the axis of rotation. And you can see that this is just omega vector. And this thing you'll recognize as the moment of inertia for point particles. And so it's in this way we recognize that for the rotating rigid body, we can use this equation, L is equal to I omega, to represent our angular momentum. Okay, great. So let's just practice that a little bit, just quickly find the angular momentum of a couple different configurations, just very easily. Let's say I have a disk and has a mass m and a radius of r. And I just like to find the angular momentum of that disk around two different axes of rotation. So I'm going to take the same disk and copy it and put it over here. It's the same disk, but I'm going to have it find an axis, the angular momentum, around an axis of rotation right through its center of mass location, assuming this is uniform. That x would be the center of mass. And then I'm going to find it around a different axis of rotation at the midpoint between the center of mass and the outer edge of the disk. So my first axis of rotation, right through the center of mass, second axis of rotation, right through the green axes or halfway point. So if this is the radius r, right here, the halfway point, of course, would be r over 2. So I'm going to assume that I know the angular velocity as this rotates around the axis omega 1, and I'm going to know the angular velocity omega 2. The actual angular velocity vectors, of course, point in what looks like the positive y hat direction. Sometimes we just like to denote this, and that gives, for the other right-hand rule, the direction. If you curl your fingers along in that direction, the thumb points the direction of omega, remember? And so ultimately, L is going to point the direction of omega for these rotating rigid bodies. So L here is equal to I times omega sub 1. And maybe I could write this as omega sub 1 in the positive y hat direction, if this is positive y hat. Assume I know omega 1, and then all I really have to do to find the angular momentum is to plug in what is the angular momentum of a disk, and I looked that up. It's 1/2 mr squared. And that would be the angular momentum. I'll call it angular momentum 1 of this first configuration. For the second configuration, it's effectively the same thing. I'd write omega sub 2 as omega 2 y hat, and the angular momentum would literally just be I times omega 2, but I'm going to give this I as sub 2 now because it's different than the first angular momentum, and I would have to use the parallel axis theorem in order to find the moment of inertia about this rotating or axis of rotation. So I center of mass is just what we used over here, 1/2 mr squared. And then I just have to look for the parallel axis. So here's the axis through the center of mass, and here's a parallel one. So they are parallel, and this is the distance d of separation. In fact, it's just r over 2. So this is 1/2 plus 1/4 mr squared, or 3/4 mr squared. So at the end, my angular momentum vector for this rotating rigid body is as follows: I times omega sub 2. I know this is very simple, just kind of warming up a little bit. What I would like to do now is just to kind of carry over with work that we've been doing before. I know when we were talking about the point mass and we were working in the conical pendulum, a lot of what we were doing was exploring the relationship between sum of torques being dl dt and finding the angular momentum and then comparing it to the torque. And in fact, we can do that kind of analysis now for the rotating rigid body. The difference is that, of course, when we consider the angular momentum, we'll want to be considering angular momentum for a rigid body if we have a rigid body, and for a point mass if we have a point mass. So we're going to be using kind of both kinds, I omega and r cross p, depending on what we have in our system. But we can still talk about this relationship between net torque and dl dt. And it's pretty easy to see that dl dt for a rotating rigid body, where I is a constant for the rotating rigid body. For a rigid body, that's what's assumed, is going to look like I times alpha. So we can see that relationship right away for this is the sum of torques equals I alpha for the rotating rigid body. So that makes a lot of sense. And now we're going to kind of use everything together. So on this next page, I have a couple of masses. Here is M2. It's just moving along on this frictionless surface. It's attached by a massless string to a massive pulley, mass M, radius R, and M1 is also attached from this other massless string, well, the same string, but remember we treat this as T1 and T2 separately because there's a mass in the middle. But the next part of the string, it's attached to it, and everything is moving M1 down, M2 to the left, and M is rotating in the counterclockwise direction. And in this problem, I'm going to call my system M1 plus M2 plus M, the whole thing. All three masses are in my system. And what I'm going to be calculating is what is the angular momentum of this system. And then from that, I'm going to calculate what is dl dt. And then I'm going to actually calculate what is the sum of torques. And from this, I'm going to be able to find a value of acceleration of the system. So right now, M1 and M2 have the same V magnitude, but they also have the same acceleration downward. They also have the same A. So you'll see where I'm writing both of those vectors on here. And similarly, I have an omega and an alpha. For the rotating body. Oops. Excuse me. So look, we have another way of calculating acceleration as a comparison value to what I'm about to do. I could have done Newton's law analysis. You know, sum of torques equals I alpha for the rotating mass. And then sum of forces equals MA for the translating masses. And if I did that, I can arrive at this result that acceleration is going to be m1g divided by m1 plus m2 plus a times m, where A is capital A is representative of the geometry of this rotating pulley. So if it's a disk, A is 1/2. If it's a ring, A is 1, so on and so forth. So I can, and I also find acceleration via Newton's law, but I'm going to find it this other alternate way. So the first thing I'm going to do is find the angular momentum of the whole system. I have effectively 2 translating point masses and 1 rotating rigid body. So I have been very careful in this drawing to center everything so that M2 is right here when I treat it like a point mass, right here in the geometric center, and M1 is right here. It should be in the geometric center of this thing. Oops, kind of shifted off a little. But so that I'm aligned with these ropes, so it's like I'm pulling a point mass directly along the line of these ropes right here. I've been very, very careful to draw it so it looks like this, because it's going to help my analysis. And if I think about it that way, then I would think about each one of these point masses having a V, one down and one to the left. And so the angular momentum of the system is actually to include 2 point masses and 1 rotating rigid body. So I'm expecting to see R cross MV twice, 1 for each point mass. So I'll give them little subscripts 1 and 2, and then an I omega for the massive pulley. So what I'm going to do, and specifically I would tell you in a problem like this, to find the angular momentum with respect to an origin, and that origin is the center of the pulley. So let me go ahead and mark that. Right here. So I'll kind of do it again in green too. So I'm finding everything with respect to the center of that pulley. So for instance, for mass 1 over here, my R vector will point from the axis like that. That'll be my R sub 1. And my V sub 1 is, of course, just this thing. It's the same magnitude for both of these. So I'm going to go ahead and draw my R sub 1 kind of officially now. Here it is. I'll make it a little thicker, actually. Here's my R sub 1. And let me redraw it over here. And it's going to have a component along the negative y hat and one along the negative x hat. The component along the negative x hat is just the radius, right, of this pulley. So I can go ahead and write this as minus rx hat. And the y direction, I actually don't know its value. So I'm just going to say it has the value of y in the y hat. You know what? Because I actually don't care about it. After I finish writing out R sub 1, you're going to see that after I take the cross product with MV sub 1, this is going to completely disappear. So I don't know why, but that's okay. I'm going to go ahead and include it in here as an unknown. If I knew the acceleration of the system, maybe I could solve for 1/2 AT squared and actually find y in a different way. So that would be interesting for me to do, but I don't need to, because it's going to come out in the cross product anyhow. And so my V sub 1, again, for the mass one is just this quantity right here, and V sub 1 is just magnitude V in the minus y hat direction. And so you can see that I have a R crossed M1 V1 here to take, which is really can be written since M1 is a constant as R1 crossed with V1. So I'm going to go ahead and take the determinant of that cross product, M1 times x hat, y hat, z hat. R sub 1 is minus R minus y 0. V sub 1 is 0 minus V 0. And when it's all said and done, I'll have 0 in the x, 0 in the y, and I will not have 0 in the z. So in the z hat, I'm going to have a minus r times minus v minus 0. all times m1. So this whole thing will equal to m1 rv in the z hat direction. Okay. So I'm going to do the same thing to help me find r sub 2 m2 v2. So let me draw my r sub 2 vector. Remember, it's with respect to this axis, and it's pointing to the point mass. So here it is. Here's my r sub 2 vector. Now I'm going to draw that more permanently now. Here is r sub 2. And for my r sub 2, I also have a similar situation where one of my components is just the radius of this pulley. I've drawn it very specifically this way, and then I don't know this other quantity, but that's okay. I'm going to go ahead and just write it as x and this as r. And r would be in the positive y hat and x would be in the positive x hat. And then the entirety of my r sub 2 would be represented as x hat plus r y hat, where again, very similarly, I also know that this component is going to disappear in the cross product with v sub 2, which points also in the x hat direction. So v sub 2 is positive v in the x hat. And so if I look at m2, r2 crossed v2, where I've just pulled the m out because it's a constant in the cross product, I'm going to get kind of something similar if I go through and write this out completely. And in fact, oh shoot, I made a little boo-boo, I just realized. V is actually pointing this way, so it's minus vx hat. Excuse me. Let me not mess that up now. And when this is all said and done, this whole thing is going to equal to m2 rv in the positive z hat. So very similar, same v, because they're connected by that rope. And what I have now are the first two components of the total angular momentum of the system, the m1 and m2, and all that's left is one for the rotating rigid body. So for the rotating rigid body, it literally is just I times omega. Using kind of the alternate right-hand rule, I'm looking at this thing and I see that it's making a counterclockwise rotation, which is associated with a positive z hat direction, which since I've been using positive y hat up, positive x hat to the right, the positive z hat is out of the board. And so I can write this as A times magnitude of omega z hat, where omega, this is definitely a positive and in the positive z hat. And so it's just a matter of finding I, and this is the moment of inertia of the object, which I already know to be A m r squared, where A is something I can just put in. And also, at this time, I'm actually going to try to get everything out of omega and write it in terms of v. So for this angular momentum of the system, I'm going to assume I pretty much know everything here on the page except for A. So I'll know V, M1, M2, M, and R, and A. So let me write that down here. I'm going to know A, M, M1, M2, and V. But I don't know omega. And remember, what I'm solving for is just angular momentum total. So at this point, I really do want to get this out of the omega. And I'm going to remember that omega is equal to V divided by R. In general, it's V tangential over little r. But when I'm exactly at R distance away at the outer radius, that's when that radius is going the same tangential speed as the string, which is going the same tangential speed as M1 and M2 effectively. So when R is equal to capital R, V tangential is the V that's associated with the speed of the string, which is the speed of our masses. So I'm going to replace omega with V over R in this case. So in total, my angular momentum for the rotating rigid body I omega, just that term, is going to be AMR squared V over R in the positive Z hat. And one of those R's will cancel for this to be AMR VZ hat. So L total of the system will all be in the positive Z hat direction. And I'll have M1 RV plus M2 RV plus AM RV. And that's the angular momentum. Now, what I'm going to do is just kind of play around with it. I'm going to take a derivative and then also kind of look at the sum of torques for the same system and use that to find a value of acceleration and then compare it to this, which I could have found using a Newton's law analysis as described. Oops, not ready for that yet. Let me give a new page. So I'm going to cut a couple of things out of here. This, and then my drawing. Let's see if I can capture the best parts of this drawing. Okay, so I want to think about sum of torques. So the first thing I'm going to do is I'm going to kind of manually just take a derivative of the whole system and say that that's related to the net torque. Before I do that, what I'm going to do is to pull out an R and a V, which is common to both of them out of this, and I have an M1 plus M2 plus AM positive Z hat. And what I'm going to recognize too is that the only thing changing with time is this V. R is a constant, and M1, M2, and AM, they're all constants too, but V gets larger and larger as the system keeps moving. So I know that it changes in time, but R, M1 plus M2 plus AM doesn't. And so the only thing that it's acting on is that V. And so dv dt, of course, is the acceleration of the system. So right away, that's how I'm able to kind of solve for the acceleration of the system eventually, is that it comes up here in the time derivative of the angular momentum. But what I'm going to do is to kind of manually look at the sum of torques by literally looking at the sum of torques for the whole system relative to this point right here, so I can compare it accurately to the angular momentum. And so I should kind of quickly redraw this, so just bear with me. I'll have a point mass and another point mass here. Yeah, kind of the system. And I'm going to do some force body diagrams now. So I'm going to call the tension acting here on this side, make it a little thicker. I'm going to call it T1. It's acting equally and oppositely, one here and one here. And here, this will be T2, equal and opposite, just like that. I also have the force of gravity, M1G acting here, M2G, a normal force acting here. I could also, I'm going to have some kind of pinning force. I'm going to assume that it's going to point something like this, and also mg acting here. But, you know, my axis is here. So right away when I look at the net torque on the system, I already know that the net torque is not going to be including P and mg. We've been over this a lot of times, but the torque associated with P and mg is 0 because their R value is 0. So only have to consider T1, T2, N, M2G, and M1G. But let me just tell you this. Normal force N and gravity, they're equal and opposite to each other because the sum of forces in the y equals 0 for this mass, so N equals to M2G. And because of that, any torque, these just add up to be 0. So they become effectively not an internal force of the system, but they don't contribute any net torque because they're acting at the same point with equal and opposite magnitude. Same with these tensions, they also are going to completely cancel out. These, however, do become internal forces to the system. And it's internal because I've opened up the system. I broadened the definition of the system since it's all 3 of these. And so the sum of force from these 2 are also 0. Same thing for T1 and T2. So in fact, the only force that contributes at all, and this makes sense, is M1G because it's the only thing driving the whole interaction. So when I consider the whole system, every single force except for mg, M1G, does not contribute to the system. And so all I have to do is find that torque. I'm going to say it's R F perpendicular times whatever direction it's in, which honestly, it's going to be causing a positive z hat direction. One way that I can see that really quickly is because I'm looking at its R value. So I'm going to redraw this X right here. And M1 is right down here. Okay, moving down with M1G. The R value looks like this for the torque. Also it's the same as the angular momentum. So it's really my R sub 1 that I had before. And when I I could take a cross product to get the torque, or I could use the right-hand rule that I taught you guys last time. You line your pinkies up with the first vector, cross it in the direction of M1G, and it's going to go ahead and point in the positive z hat direction. You can see it. But you know what? Maybe I should take this cross product. I already have R1 written out. Where are you, R1? Here you go. So let's go ahead and take the cross product. Let's not do this. Let's not do this way. Let's just take the cross product. R1 crossed with the force minus M1GY hat. So let's look at the determinant. Minus R minus Y 0, 0 minus M1G 0. And nothing in the X, nothing in the Y, only in the Z. And in fact, this will be Z hat R M1G when it's all said and done. Positive. And so the net torque is equal to R M1G Z hat via manually looking at the sum of torques and taking it for the whole system. But I also have another definition for the sum of torques that comes from this definition from angular momentum, and I have it here. And these are equal to each other. R M1 plus M2 plus AM times AZ hat. And it's using these equations that I can now solve for A. A will be equal to, the R's will cancel, as kind of postulated earlier, something that I could have found with a Newton's law analysis. So let's just verify that again. Yep, here it is. So you can also do the Newton's law analysis. We were very close to doing it anyhow, because we did all the force body diagram and everything to verify that that A is the same. All right, very cool, you guys. So let's move on, because this next topic is very important. We're going to talk about conservation of angular momentum. So very similar to what we've talked about before, we've talked about this idea for linear momentum. Of course, you guys remember. We rewrote Newton's second law, the sum of forces dp dt, and we said if this is equal to 0, then momentum is a constant, or it's conserved, and we say that initial momentum equals final momentum. Well, the same thing holds for conservation of angular momentum. If there's no external torques on the system, these are external forces too. Internal forces just go away, and so do internal torques. We just saw that happening with our T1 and T2. If there is no net torque on the system, then dLdt is 0, and then angular momentum is conserved. So we have a similar kind of condition. Let me write it out. If the net torque on the system equals to 0, then angular momentum is conserved. So angular momentum can be really interesting when it comes to conservation, because you can have a lot of situations where you don't really need to have a collision or anything like that for it to be interesting looking. So here's kind of a standard example. You have an ice skater, and here she is. She's rotating around. This is her axis of rotation through her center of mass. So let's say her center of mass is right here in the center of her body somewhere. And it may not look like it, but her arms are out and they're evenly spaced. Right? They're evenly spaced and they're out right now. And she's spinning around here on this leg. And, you know, she is not rotating right now because, I mean, she's not falling over like this or falling over this way. She's not rotating in the YX plane right now. She's just rotating about the Y like this. And the reason for that is because if I quickly look at, let's say I treat this as the place that she would pivot to rotate this way or this way, I know that it's actually going to be gravity acting on her, which, let's say gravity acts like this. That's her mass, and maybe there's a normal force acting on her too, but for right now they're kind of equal and opposite and nothing is going on. Well, what she does is she brings her arms in this very even way. So they start out on the very outer edges here, but next thing you know, she'll bring them in evenly to here, and then bring them in evenly again to here, until finally they're just right here evenly with respect to one another. She's brought them in. And what she's done is she's kept her center of mass right here the whole time. Her center of mass has not changed as she brought her arms in very, very evenly. And so the whole time, gravity has acted at this center of mass as she brought her arms in up until this very end. And she does that to avoid having a net torque acting on the system. If for some reason she brought this hand in more quickly and this hand was still out here, then her center of mass would have shifted a little bit to this direction, and she would have, you know, with respect to this axis, had an RMG. That would have changed. There would have been a net torque, and angular momentum would not have been conserved. But if she's careful and she brings those hands in very carefully, she can do it in such a way the net torque on the system is 0. And the results are super cool looking. Her angular momentum is conserved, but her moment of inertia has changed somehow or another. And what that does is it changes her speed. I know you guys have seen this before, but let's take a look. And she goes faster. Now, she was translating a little bit at the end right there. She was translating a little bit. Let's look at somebody else doing it here. Let's see what I got.
Go.
Oh, it's Professor Harris.
So earlier this semester, the last test cycle, we introduced the topic of the conservation of linear momentum. Remember, during collisions, elastic or inelastic momentum was a quantity that is conserved. Well, we just introduced this idea of angular momentum, and so I want to do a little demonstration here to see how that plays out. So just like a figure skater, I'm going to start with my hands out wide. Right, so now I have some angular momentum, and now as I bring in my hand.
See, he goes faster. You see how he's doing it evenly? He brings his hands in. Yeah, let's bring it. Let's look back. He tries to bring them in evenly. And he really is just kind of moving faster. And that is the conservation of angular momentum in play. In fact, this is a rotating rigid body for the most part. And we're going to work a problem that treats these hands as little point masses, because actually they're moving in, and we should kind of discuss that. But treat our hands as point masses and moving them in such a way that the center of mass is kept along that line allows you to say that the angular momentum before equals the angular momentum after the collision. Not a collision, sorry, after the change. And what happens is, in this particular case, in a very loose way, okay, because the angular momentum vector, you guys know angular momentum is in the direction of omega. Omega's direction in this case is also going to be in the positive y-hat direction for both of these. So when I write this out, I would have I naught omega naught y hat equals I final omega final y hat. I don't have any kind of point masses to treat right now. This is still supposedly kind of one body. My next problem, I'm going to, like I said, I'm going to treat the hands as point masses and work this, and the body as a cylinder. I'm going to work the whole system. But for now, I'm just treating this as a rotating rigid body where initially it has one angular velocity and one moment of inertia, and then finally has a different moment of inertia and a different angular velocity. And I'm able to say I naught omega naught equals I final omega final, and omega final, solving for it in terms of I naught, I final, and omega naught, really looks at this ratio of I naught to I final. And when her hands are out like this, her moment of inertia is larger than when her hands are in like that, because the farther away the mass is, the larger the angular, the farther away the mass is, the larger the moment of inertia. So I naught is larger than I final, which is smaller. And this is why, via conservation of angular momentum, omega final is larger than omega naught. In fact, she spins, as long as she meets this condition that the sum of torques are zero on the body, she conserves angular momentum and can spin faster. It's very cool. So we are going to work this problem, just kind of treating this in ways that we understand, which is like saying the body of our ice skater, or Don Harris, is a solid cylinder. And at first, Don Harris's hands, or the ice skater's hands, are out some distance away, but I'm going to treat the hands as point masses. And they're attached to these rigid rods that somehow I can move back, and I can slide this point mass along to bring them in if I want to. So this is not included in the moment of inertia. It's just a massless line. But I have 2 point masses here. They're a distance of 2r away from the very edge of the solid cylinder, and the solid cylinder itself has a radius of r and a mass m. And initially, it has an angular velocity of omega naught. Here it is describing the motion, but here's the actual vector, right? And eventually I'm going to bring those point masses into the very edge that I can of the solid cylinder, r away from the axis of rotation, and I'll be talking about a different omega final, which presumably I'll be going faster for, so we should be able to see it. And let's talk about conservation of angular momentum. And I am going to go ahead and treat this for point particle. 2 point particles, and a rotating cylinder. So my initial angular momentum, let's take a look at it. For the entire system of 2 point particles, my gosh, what am I writing here? Is R cross MV plus I omega. Now, if this is rotating around like this, I've got to tell you guys that this mass right over here on the left-hand side currently has the tangential velocities actually pointing out of the board. So the V is in the positive z-hat direction right now. And right now on this side, it's going into the board because it's spinning around like this. So this one is going into the board, this one's coming out of the board, and the velocity right at this particular moment is minus v z hat. Really, it's in the tangential direction, but let's just pretend like for this moment, here it is. My r vector for each one of these, and let me kind of give them a good subscript. So if this is m1 over here, and this is m2 over here, they both have the same masses. It's true, they're the same hands. But I would want to look at r and then mv. Well, here's my r. It's from here, let's say from the axis of rotation here. This is my r vector. And my mv, well, it's just multiplies the v vector, which points out of the board. And if you do the right-hand rule, you'll see the whole thing is going to point in the positive y hat. Same with this one. Here's the r vector that it has with respect to the axis of rotation. If you cross that with mv into the board, line your pinky up with the r, line your pinky up here, fold your hands in such a way it goes into the board, and your thumb should be pointing in the positive y hat. Both in the positive y hat. So is my omega in the positive. Everything here is in the positive y hat direction. And well, everything is exactly perpendicular with respect to one another too. R is exactly perpendicular to a vector that points out of the board, and R here is exactly perpendicular to a vector that points into the board. And so everything coming out of this is just going to be R1 M1V y hat plus R2 M2V y hat, because they're exactly perpendicular. They're going to be a sine of 90 degrees for the cross product. And this will just be I omega y hat. So that's L of the system before. I should be writing in omega naught here, so let me do that. And I'm going to go ahead and replace my V's with omega naught times R, the distance away from the axis of rotation. So this R1 is what I'm talking about here. That's how far I am away from the axis of rotation. Same with this R2. They're the same for both of them. R1 equals to R2, which equals to this R. In fact, my R1 is 3 times R away. So all of these have a 3R, M1 omega naught times 3R in the y hat, and there's actually 2 of them contributing in total, plus moment of inertia times omega naught. And the moment of inertia of a cylinder is 1/2 mr squared. And so in total, I have 6r. Just kidding. These m's are all the same. I have 2 times 3 times 3. I swear I can do math. That's 12 mr squared omega naught in the y hat plus 1/2 capital mr squared omega naught in the y hat. And so I can simplify this a little bit more. I can pull out, let's see, an r squared and omega naught. And that is the initial angular momentum of the system. Now look, I could have done this a different way. I just feel like I should tell you that this is equivalent to writing this as I omega naught y hat, where I is for the system. I could have written I as the moment of inertia of the cylinder plus the moment of inertia of each of the individual point masses. If I had, I would have had 1/2 mr squared plus 18 mr squared. Oops. Did I mess up somewhere? Yep, I sure did. This was 18 too. I'm so sorry, guys. 3 times 3 times 2 is not 12. It's 18. So excuse me. I did it kind of a harder way just to show you that they're equivalent. treating this as a point mass and a point mass angular momentum is the same as kind of adding it on into the moment of inertia here. So interesting. I could have just written, found the moment of inertia, and that would have been it. Okay, so that's the initial angular momentum of the system. Let's find the final. So let's do it the easy way this time. Let's just find the final moment of inertia. It'll be the moment of inertia of the cylinder plus the point masses. And I already know they have the same mass, but now they're a distance of r away instead of 3r away. And so the moment of inertia final is 1/2 mr squared plus 2mr squared. And so if I write this as I final omega final y hat, I can set these two values equal to each other. Conservation of angular momentum tells me that 1/2 mr squared, oops, 1/2 m plus 18m r squared omega naught y hat will equal to omega final r squared 1/2 m plus 18, 1/2 m plus 2 m, where I've pulled out the r squared y hat. So I've just plugged in the final angular momentum. I pulled out the r squared multiplied by omega final. And from this I can solve for omega final in terms of omega naught, just like I did before. The r squareds will cancel from here. And what I'm going to have is all of this is going to be a fraction multiplying omega naught, 1/2 m plus 18 little m divided by 1/2 m plus 2 little m. So if I had been smarter, I would have told you that maybe m was equal to 1/10 of the total mass or something like that, so I could kind of cancel everything out. Maybe the hands, people have heavy hands. Yeah, let's say 1/20th. And I could have seen kind of what fraction this ratio had. I guess we should do that. So if I do that really quickly, 18m will become 18/20ths of m, and 2m will become 2/20ths of m, giving a common denominator everywhere. What I'll end up with is 28/20ths m divided by 12/20ths m, all times omega naught. So this would be, let me move this out of the way. This would be 28/12ths omega naught, or that's 14/6 or 7/3, or about 2 1/3 times as fast as it was initially. So a lot faster. Okay, great. So that's an example of conservation of angular momentum. In your homework, you're going to look at kind of a simple problem where you have a mass that rotates around its axis like this. And you're going to drop another mass, a smaller disk, on top of it. It's not rotating at first, only the bottom one is. And then you're going to drop it on there, and then they're going to stick together and rotate together kind of after the collision. And this will be an example of for a rotating rigid body where you would use this relationship. There's a new moment of inertia with this thing as it spins versus what it was originally. And you should be able to solve it just for the rotating rigid body in that way. So, and that's an example of conservation of angular momentum. Of course, you have to be able to justify why the net torque is 0. So you'll spend some time thinking about how the force of collision is an internal force on that system and how the center of mass stays in the same place. And so there is no net torque on the system when the system is both disks. Shoot, maybe I should draw that really quickly. As they collide, there would be a force of collision on this guy somehow, but the equal and opposite force of collision is here. since it's rotating through the center, that means that, whatever torque that I feel from this guy, the equal and opposite one will be felt from this bottom guy here. And since the center of mass has been kept along this line, because of the way that this system is, there is no torque from mg, where the axis of rotation is through the center here. So there is no net torque on the system for that particular case. I like to work this problem even though it is a lie. All right, so let's see how much time I have here. Oof, I've been going for almost an hour. Okay, but that's okay. We're going to work this problem even though it's a lie, because it's a good example of thinking about meeting the condition of the sum of torques is zero. So a lot of times they do this in this kind of problem. And they expect you to make a certain amount of assumptions. So I shouldn't say this is a lie. I should say you have to make assumptions to actually solve this problem using conservation of angular momentum. Just sometimes I hate that kind of thing because it's not always obvious to me. So the idea is that this is the positive y hat direction, maybe this is the positive z hat direction, and positive x hat is like this, right? So you're spinning this axis around, it's pinned through this center, this solid cylinder. It initially isn't spinning, but it's going to after it has a collision with this little mass, sticky mass of clay right here. In fact, it's sticky, so when it collides with the solid cylinder, it's going to stick to it. And then the whole thing is going to rotate around like this, around the z-hat axis. That makes sense, right? It's going to use conservation of angular momentum if you take a certain set of assumptions. And what that assumption has to do with is the fact that you need to meet that condition that the net torque is equal to zero. So a lot of times I spend time thinking about the forces and whether or not I meet this condition for these kind of problems. But this is a conservation of angular momentum problem if you make the right set of assumptions. So let's look at the problem just one more time before I get sidetracked by that. So there's this line, and they're giving you a reference of this distance d, which relative to the center of the cylinder, that mass is coming in at that y distance relative to the center, and d is less than r in this case, because here's the radius and here's the distance d. And this mass is coming in with some linear velocity and linear momentum, m times v sub I, and this thing initially isn't spinning, and then it sticks to it, and the whole thing starts to spin together. Now, what I'm going to do is to define my system as m plus big M. Big M is the mass of the cylinder, little m is the mass of the clay, is my system. And then, presumably, as the clay is hitting the cylinder, there's going to be a force of the collision acting on the big cylinder, but there'll be the equal opposite force of collision acting on the mass, m, the clay. So these will get canceled out, become internal forces to the system, and that means that they're also not going to contribute to the torque. Because really I'm looking for these external torques to be zero, not internal ones. I know that internal forces will be zero, or give internal torques too. So what other forces act on my system? Well, I'll have mg acting here. And I have some kind of pinning force, right, acting here. I should kind of make that a little bit more arbitrary, actually. Let me make it a little thicker too. So here, arbitrary direction. Here's a pinning force because it's pinned at the center along this axle right here. I'll have the force of collision, which I've already negated. And then there's also gravity is going to be acting on this thing. So, sorry. There is a normal force acting on this mass, but then there'll also be the equal and opposite normal force acting over here. So normal forces become internal, but there's still kind of gravity and gravity acting here. So the reason that this is a lie is this. The sum of torques is not actually equal to zero because what happens is the center of mass changes. So let me just show you this drawing kind of without all of the internal forces on it. I would have kind of P acting at the center, mg acting here, and then there's this little kind of gravity here, and after this thing sticks to it, what happens is that the center of mass is changed to be somewhere along this line. So maybe m is smaller than m, And if that's the case, then maybe the center of mass changes to this location, which means that M plus mg is really acting here. And there is, in fact, a net torque on the system relative to this point, because there'll be an r vector here and an m plus mg here. Because otherwise, of course, mg and p, they don't contribute at all because they're acting at the axis of rotation here, right? So there is no net torque from these two, but there really is one from this mg, or when you think about the center of mass has changed, there is, in fact, a net torque on the system. So that's why this is a lie. You either have to make a couple of assumptions to kind of move forward with this problem. And one of the ones that you could say is that maybe m is much, much less than m. If that's the case, then the center of mass would still be approximately right here in the center. So that's one approximation that you can make. So center of mass is at the same place. Or maybe a more realistic approach would be to say that this axle actually has the axle that goes through the center right here actually has a certain amount of thickness to it. So as maybe there's this additional gravity force on the system, or maybe as the center of mass tries to shift, maybe to be here, and there's a force, and therefore a torque from gravity because it's not acting at the center, maybe what happens is that there's a pinning force that reacts that's not exactly at the center, a new y component of a pinning force that acts. That's not exactly at the center either, to counteract the torque from gravity. So you'd have to make one of those assumptions to meet the condition that sum of torques equals to 0. So previously, maybe you had a y component of a pinning force like this, but as soon as you added the mass stuck to it, maybe there was a new one and it acted a little bit to the left of center over here, maybe. Okay. There's also going to be an x component of the pinning force, but I'm going to come to that later. So this is a lie, or you have to make certain assumptions to work this problem. So I'm going to erase everything that I have here. And I guess I'm going to make the assumption that there's actually a thickness to the axle, or that m is much, much less than m. And now I'm going to solve the problem assuming that the sum of torques is 0. All right. Because otherwise it's a decent problem. It says, find the angular speed of the system after the clay strikes and sticks to the surface of the cylinder. So kind of the before picture is you have that lump of clay coming in right here. It's about to hit it right now with some mv, that's the linear momentum. And my cylinder has an omega equal to 0. But then after the collision, that's when they're stuck together and the whole thing is now moving with some omega. And that's the question, what is the omega relative to that center? And so if the sum of torques equals to 0, then I can say angular momentum is conserved. Angular momentum is conserved. Well, great. I have initially only one kind of angular momentum. It's from the point mass. So I have a translating point mass and a rotating rigid body. So I can have angular momentum from the point mass and angular momentum from the rotating rigid body, but this one is not moving, so it has no I omega. It's equal to 0. There's only angular momentum initially. From the point mass, and I'll even write it out here just to be clear. Oops. I have two different kinds of objects here. Well, this is kind of a lie because after the collision, in fact, after the collision, this is stuck together. So I include the point mass and the cylinder as my rotating rigid body now, right? So there is no angular momentum for a point mass after the collision, right? Because they've stuck together, and it's only a rotating rigid body now. But before the collision, I have the possibility of both. Maybe this one was rotating, but it's not. So there is no initial angular velocity. There's only an incoming initial momentum from the point mass. So really what this reduces to is R cross M V naught equals I final omega final. So let's say what's known in this problem. The little mass is going to be known. The initial velocity, I'll call it V naught, is known. D is known. And M and the radius. And you're told this is a solid cylinder, so A is equal to 1/2 when you talk about the moment of inertia, AMR squared, about the center of mass. So let's go ahead and move with this here. So I'm going to find an expression for my initial velocity. It's a vector, and it's coming in the positive x hat. Here's the positive x hat. Here is my velocity. I'm going to find an expression for r right before it hits. So maybe I'll make the mass closer here for before. And relative to the center or the axis of rotation, this would be my r value right here. And my r value, let's see, it looks like this. It's going to have a component in the y that is just this distance of d, and it'll be r in the x. So I know d, I know r, so I can kind of fill out this triangle here. This is d, this is the radius right before it hits. So this would be r in the minus x hat as a vector, and in the positive y hat d. So my r vector is minus rx hat plus dy hat. And I'm going to go ahead and take a cross product now between r crossed with v naught, all of that times m, and that will equal to m times, and I don't even need to do this anymore. I can just see r cross v naught is going to be number one in the minus z hat direction, and only d is really going to survive this. So you can prove that to yourself. And that's the left-hand side of the equation here. It's just going to be, I guess I'll write it as dmv in the minus z hat direction. The final angular momentum, since it's moving this way, is a clockwise rotation, so it's into the board is the direction of the vector, which into the board here is the minus z hat direction also. So for the final angular momentum, this is going to be omega final in the minus z hat direction. So really all that's left to do to kind of solve this problem is to find I final. Well, remember, I final is a rotating rigid body that also includes this point mass right here. So I have the moment of inertia of the cylinder plus the moment of inertia of the point mass. This is 1/2 mr squared plus mr squared, where r is how far away it is, and hell, from the axis, it's actually at a distance of r away. So this is also r squared. So I final is 1/2 m plus m r squared. So putting it all together, L naught equals L final minus dmv z hat equals minus 1/2 m plus m r squared omega final z hat. And I can solve now for omega final from this, getting rid of the z hats and the negative sign. Oops. Okay. And that's the first thing that I'm solving for. The second thing I'm solving for, you can see it says is the mechanical energy of the clay cylinder system constant in this process? It's asking if energy was conserved. And I'm immediately like, no, this was an inelastic collision. I know it's not conserved, but let's prove it really quickly. Was the kinetic energy before the collision, is it equal to the kinetic energy after the collision? Before the collision, I just have 1/2 mv squared. After the collision, I have 1/2 I omega squared, right? Only translational, only rotational. The left-hand side is easy. All I have to do is put in this V naught over here to make it official. For omega squared, I should actually come back to here and cut out my omega. And I'm going to be inputting my omega final into here. I'm also going to need to remember that this is my I value here. Okay. That's my I right there. So it might be easier for me to write this right-hand side as 1/2 I dmv squared divided by I squared, which is me just squaring dmv divided by I and inputting here, just so I don't have to worry about cancellation, because this is a little bit easier to look at. And I'll input the I now. So this is also V naught right here. And I'm really asking, does the left-hand side equal the right-hand side? Well, it's hard to see right now, but it doesn't. But I do see that I can pull out a 1/2 mv naught squared from this thing. I have a 1/2, one of those m's and the whole v naught squared. And I'll be left with m d squared over 1/2 m plus m r squared. Are these equal? Well, they're equal, if this is 1. So does m d squared equal 1/2 m plus m r squared? Well, let me bring this 2 over here. First of all, d is less than r. That's number 1. Number 2 is m is greater than m. It's just general in this problem. And so this is more than 2m. In fact, we probably would have used the approximation if we hadn't used the other one that is much, much larger. So in fact, this is more than 2m, and this is more than d. So r is greater than d, and m is greater than little m. So the answer is no. It's not going to happen. The only time it would happen is if it hit right at the very top and the masses were identical. Part C of this problem, let's flash back to it, says, is the momentum of the clay cylinder system constant in this process? Momentum. They're talking about is linear momentum conserved in this process. The condition for that would be that the sum of forces would have to be 0 on the system. And I'm going to go ahead and argue that it's not constant. And in fact, what that comes from is if I think about during the collision, and I just think about the cylinder, the big mass, not the clay hitting it, and I think about all the forces that act on it during the cylinder, during the collision, I know that there's a force of a collision maybe acting on the system like this. I know there's also gravity, and I know prior to, so this drawing is prior to the collision, that I would have to have P equal mg, and so there would only be a y component of P. There'd be only a pinning force and gravity, and so P would only be in the y. So there's a pinning force now, but during the collision, what actually happens is that there becomes not just a y component, which increases as discussed, but there's also an x component. So that has to happen in order to compensate for the fact that there's a collision force coming in. So it doesn't create a net torque because it acts at the center. It doesn't create a net torque because it acts at the center, but there is a net force. So it has to be, otherwise this whole mass would be translating to the right when it collided. If it wasn't pinned, it would just move to the right. So there's actually no way to meet this condition, so no. Okay, so let's move on to one more kind of problem that you might see. And here it is. This is dealing with the idea that we can have collisions where both linear and angular momentum are conserved. So this previous problem, we made the point that since it was pinned at the center, part C of this problem made the point that because it's pinned and it's not just free to move, that when it has a collision, that the pinning force will create an equal and opposite force to the collision, and therefore linear momentum is not conserved. But if it was not pinned down, I could have a situation where I did have the sum of forces 0 and linear momentum and angular momentum were conserved. And this is that kind of problem. It's very specialized. So for instance, the y-hat direction is supposed to be out of the board here, and this is supposed to be on the frictionless surface, like a horizontal surface in the xz plane. And this is actually an example in your book. I think it is, let me just look very quickly. Example 11.9 in your book, at least in my version of the book. They kind of go through this in more detail than I'm going to, okay, to be honest. So this is an impact that's happening on a frictionless plane, and you have a little point mass that's coming in with some initial velocity v, which means that it has a, it means that it has a momentum v as it comes in. And it's coming in right at the very top here. So what happens is it hits the top, but then it kind of keeps on cruising past it. So like it hits it and then is able to move past, because maybe this thing starts to move just a little bit and it's still moving forward with linear momentum along the same line. So that's an approximation. But this is the before collision and this is the after collision picture. And you can see that after the collision, what happens, because it just nicked the top of this thing, is it starts a rotation. God, I swear I've been in a car accident like that before. Yeah, it causes a rotation just like that. So after the collision, there's a rotation that occurs. But what actually happens is that the center of mass is actually moving too. So maybe this is sometime later, and maybe this would be like the initial kind of position of the collision. And what's happening is that the center of mass is just kind of moving along here. Maybe we should make that bigger. The center of mass is moving. V center of mass. V center of mass. So this object is both translating and rotating simultaneously after the collision because it's not pinned down. So there is a net force from the collision that acts on the system, right? The sum of forces allows for acceleration of the center of mass at that time, and after that it's just going to cruise along with V center of mass. So because it's not pinned, it moves. Now, what I'm going to justify to you really quickly is that for something in the absence of any external forces or external torques acting on the system will naturally translate, the center of mass will translate, and it will rotate about the center of mass, not some other point. So this is something we probably intuitively understand. Maybe we flicked something on its end before, and we watch it rotate around its center of mass. But why it does it is a good question, and I'm going to kind of loosely justify to you that that's the case. So the way that I do that is I'm just going to say that naturally in systems, you're going to see that systems will choose motion such that energy is minimized. And this is something that I've learned as I've gone on in physics and probably any other science with systems that you talk about, is that a system will choose a state such that energy is minimized. So this is a very loose justification of why something would rotate around its center of mass, but let's say that I have two masses. They're equal masses, m and m, and I'm going to mark an axis of rotation arbitrarily. I don't know where it is, so I'm just going to say here's an axis of rotation. I'm going to try to find the best one, but for now I'm going to say that it's a distance x from this first mass. And if the distance separating them is L, then this distance is L minus x right here. And I'm going to say, where is the best axis of rotation? Is it the center of mass? Because the center of mass for two equal point particles like that would be in the center, right? And so what I'm going to do is I'm going to find an expression for the moment of inertia based on x and L minus x distance away from this axis of rotation. And what I'm going to find is that if I minimize the moment of inertia with respect to x, that it's going to say that it wants the axis of rotation, or x, to be at L over 2. So let's find the moment of inertia of this system. It's 2 point masses. So here it is. The first point mass is m, and it's x away from the axis of rotation, which again is marked in blue. The second mass is m also, and it's L minus x away from the axis of rotation. So now what I'm going to do is I'm going to take a derivative of I with respect to x. You know, if I plotted I as a function of x, it's going to look like this, just so you guys know. Oh, sorry. Well, it doesn't exactly hit that 0 mark. But it experiences a minimum. So I know if I take a derivative of x of I with respect to x and set it equal to 0, I'm talking about a minimum. And where does that occur? Well, let's find out. The first derivative of the first term will give me 2mx. The second derivative will give me 2m L minus x times minus 1. So that minus sign allows me to bring that to the other side, and I'll get that happens when 2mx equals to 2m L minus x, or 4mx is equal to 2ml, or when x is equal to L over 2. So the moment of inertia hits a minimum when x is equal to L over 2, or is at the center of mass location, L over 2 away in the center. Now, this is related to energy, because if I was rotating this thing without any kind of external forces, I is in here, I being smaller lowers the energy, and that's the thing. Every single time, in the absence of some kind of external force or torque, it's going to rotate around the center of mass. Okay. So this is just a brief justification by saying moment of inertia minimized means kinetic energy minimized, and that in a system, energies will tend to choose a state where it's minimized if it has a choice. And so when I have something that is in the absence of being pinned or forced to rotate around a certain point, it's going to rotate around its center of mass location. So interesting. So number one, that makes this problem interesting. Number two, what makes it interesting is that we also are going to have kind of a motion of the center of mass too. This thing, the center of mass translates, and then it also rotates about the center of mass. So it should be making you think of Chasles' theorem right now. And so if I talked about angular momentum conservation, so let me justify that really quickly. So this is going to be my axis of rotation, this center of mass here. So if I have a force of collision, maybe during the collision, there's a force this way. During a collision, there's a force the other way on my system, which combines of both masses. I would have an R cross F and an R cross F that would exactly cancel each other out. These become internal forces to the system, and so the collision force does nothing. Because this is in the XZ plane, I'm not really concerned around where the center of mass is in terms of it making a net torque on the system, because the normal force will always be counteracting gravity here. So even if these had stuck together, it would have changed the center of mass of the system, but it wouldn't give me a net torque on the system because there would be a normal force supporting it from underneath that would counteract it. So because of the particular plane that it's in, it's not like the other problem in that way. So I do have conservation of angular momentum. And in fact, I'm also going to have conservation of linear momentum in this case too, because there was no net force acting on the system during the collision. And that's because it was not pinned or hinged. It was free to move. So just let me back up really quickly. These forces were here. But when I think about just this object, and I think about the force, it's not hinged here, so it can't give me an X component, or pinned here, it can't give me an X component to counteract this. And so it just moves instead. So the net force is 0. That's why it's moving. And that's why I'm using conservation of linear momentum too. So as I work through this, I would say, okay, well, initially my rod is at rest, so I would just have little m times v would be my initial momentum in the x. And then my final momentum would be the mass of the rod times the velocity of the center of mass plus the little mass times v sub f. So let me just back up and have a look at that. This rod has a mass of big M and length L. After the collision, it's moving, so like a point mass, because it's linear momentum I'm concerned with right now, M times V center of mass. After the collision, that little mass is moving with some V final that I don't know. And before the collision, I just have M times V. Everything is in the X direction, and I've accounted for everything here so I could get one equation. For conservation of angular momentum, I would just have R cross MV for the point mass because my rod is not moving initially. And then after the collision, I would have R final crossed MV final for the point mass, but I am now rotating too. And in particular, I'm rotating about the center of mass, and that will always be the case of this object. And so I get one more equation that I can use. So you should look at that example in your book. It also tells you that it's an elastic collision, so it gives you a third equation to use. And it takes you through a whole analysis. I just want to talk really quickly about a homework problem that you guys have, which is similar to this. It's one where you have two disks kind of on a plane and they come at each other. You have, let's see, M2. It's a disk on a horizontal surface that's frictionless. So we are on a frictionless horizontal surface too. And you have M1, another puck, I guess is what they call it, coming in at it. And I didn't draw it that well here, but it's they're supposed to kind of line up exactly. Like the top of M2 is just right at the bottom of M1. You can't really see it, but it's supposed to line up exactly. And M1 is coming in with some velocity V. And then it collides and it says that the rims just barely touch. And so M2 is going 0. The rims just barely touch, but that there's glue on the rims. And so after the collision, they're actually going to be moving together. And they're glued together after the collision. And so what happens is this whole thing will then start to rotate. And the center of mass will start to translate too. Just like in our previous problem that we were just looking at. But it should be known that this thing is rotating about the center of mass. So part of this problem is finding the center of mass. Because the center of mass for M2, of course, is in the center. It's a uniform disk. And the same with M1. But then if you treat these as point particles, that means that their mass, the center of mass of both of the objects are somewhere in the middle of this line right here. It's going to end up being like, for mine, it ended up being like somewhere around here for the new center of mass. So that thing rotates around the new center of mass for reasons we've just justified before for energy minimization. And so this problem says, number 1, it says find the angular momentum relative to a point about the center of mass. And then it says, find the angular velocity, the magnitude, I guess, with which it rotates about the center of mass. So this is going to be conservation of angular momentum for sure. And actually, you could talk about conservation of regular momentum, but you actually don't need to in this problem. You don't even have to use that for this problem. So this is a homework problem, so I guess we're going to go through it right now. So first thing I want to do is to find the center of mass, because otherwise I'm not going to be able to find L relative to the center of mass. So I'm going to treat M1 as a point particle, and I'm going to treat M2 as a point particle as well. And I'm going to find them relative to the center, to an origin. I'm going to right here on M2. So I'm going to find Y center of mass. And remember, it's the sum over all of the M and the sum of M sub I, Y sub I vector. The sum of both masses are M1 and M2. And then this would be for M1, it would be this distance away here, which if you look, center of mass to center of mass, it's just the addition of the radius of both of these, which is a given in this problem. So R1 and R2 are known. So are M1 and M2. So this distance is just R1 plus R2. And so M1 is R1 plus R2 in the y hat. And then M2 is actually right at the origin right there. So it's 0 in the y hat. So the center of mass of the object is literally going to be M1 R1 plus R2 divided by M1 plus M2. Now, for my values, not necessarily yours, but for my values, M2 was equal to 3/2 M1, and R2 was equal to 3/2 R1. This really kind of simplified down what I had here. And I had that M1, R1 plus R2, well, that was just 5/2 R1. And M1 plus M2 is just 5/2 M1. So this whole thing ends up being just R1 in the y hat. Also, clearly R2 is greater than R1, so I'm just if this is R2, I'm at some point right before it at R1 away from the center of this thing. So the center of mass, for me, because of these relationships, was exactly R1 in the y hat. You guys probably don't have that, so you might have to actually plug those numbers in. But this was true for me, for my values. But it gave me a good idea to see approximately where the center of mass is, so I'm going to go ahead and mark it here. It's around here for me. And so if this is the center of M2, mine was about R1 away, and that was equal to the Y center of mass value. And so when I move over here, it's still around here. That's where I kind of predicted it earlier. And now it's rotating around this point. So what I'm looking for is the angular momentum relative to this point. So there is going to be conservation of angular momentum. One of the reasons that I know that is because the only forces that act during the collision are going to be equal and opposite, and they're going to become internal forces. And so, oops. Initial angular momentum is going to equal final angular momentum. I just have to find one of them. So you know what? I'm going to find the initial angular momentum. It just wants any of them. So great. Initial is easiest to find because initially, this is my picture. This guy's not moving, and there's only translational momentum happening, or angular momentum initial will be R cross M1V, and there won't be any rigid body rotation. And so at the time of the collision, it actually looks more like this, right? My point mass, let me make it kind of big, my point mass M, here it is, right in the center of itself. This is kind of more what it's going to look like during the collision, is this configuration. So this will be my R1 vector. It will be the distance from the center of mass to the location of M1. So it's going to be R1 plus this distance. Well, R, gosh, I keep doing that. R then will be equal to R1 plus the difference between R sub 2 and your Y center of mass. My gosh. So, and that will be in the Y hat direction. And this is just the magnitude. And let me just make sure I'm not lying about that. This is R sub 2 minus your Y center of mass will give you this distance plus R sub 1. Great. So for me, since this value was R sub 1, it looks like my R vector is actually just going to be R2 in the Y hat. Yours will be different, probably. You'll have to plug in your value of Y center of mass. And then I'm going to cross that with M1 times V. And V is a known here. My gosh, what kind of person am I? V is a known also, thank goodness. And so you're able to say, well, R cross M1V is actually going to point, after you do the determinant or the right-hand rule with your hand, is going to point in the minus Z hat direction. Largely because I know that R is in the Y hat and V is exclusively in the X hat direction, so perpendicular to both of those is the Z. And this is going to be, for me, R2 M1 times V. So that's enough to give me the initial angular momentum, part 1. Part 2, I'm going to have to use the fact that angular momentum was conserved here. And I'm going to have to look at I omega relative to this center of mass location. So let's look at the conservation of angular momentum piece now. L naught equals to L final. Initially, I only have a point mass. R2 MVZ hat, M1 VZ hat. Finally, though, I'm going to have I relative to the center of mass omega plus, I'm actually translating too, right? The whole combined puck thing, it's rotating, but it's also the center of mass is also translating too. So I'm going to have R relative to the center of mass cross M V center of mass. So treating this part as a point particle moving. But check this out. Because I'm finding everything with respect to the center of mass, that means my center of mass is literally 0 away. So this is just 0. I don't have to consider the fact that it's translating because I'm looking relative to the center of mass right here. So all I have to do now to find omega is to find the moment of inertia of the center of mass, rotation around the center of mass axes. So let me go ahead and mark. Here's my center of mass, and I have a axis through this, right, because I'm rotating about the center of mass right now. So I have to find the moment of inertia of this object about the center of mass, and it's a composite object. Moment of inertia of the upper disk, and moment of inertia of the second disk about the center of mass. So here's the upper disk, M1, and it has R1, right, as the radius. And so it's a disk, and so the moment of inertia will just be the moment of inertia through the center of mass plus md squared. I'm going to have to use the parallel axis theorem because I'm not looking through the moment of inertia through the center, I'm looking at it through the center of mass right here. So what I'm going to need to know is the distance from the center of mass location the disk by itself to the new center of mass. I'm going to call that D. And D is going to consist of radius 1 plus this difference in distance, which is R2 minus R1. So D is going to equal to radius 1 plus R2 minus R1. So again, it's just R2 for me. For you guys, you'll be inputting into here, D will be equal to R1 plus Y center of mass minus, plus R2 minus Y center of mass. For me, that Y center of mass was just R1, remember? So my D is R2. So for the moment of inertia, I would write this as the moment of inertia of a disk around its center of mass, going house M1 R1 squared plus M R2 squared for my values, because this is my D. For I sub 2, it's the same thing, except for now I'm considering this disk is 2, this is its center of mass, and so I just need this distance D away, which remember we found to be R1. So for I2, this is 1/2 M2 R2 squared plus M2 R1 squared. And so the moment of inertia of both of them are 1/2 M1 plus M2 R1 squared plus R2 squared plus M1 R2 squared plus M2 R1 squared. Wait. No, I've done something wrong here. I just tried to shorten things. I shouldn't have done that. 1/2 M1 R1 squared plus M1 R2 squared plus 1/2 M2 R2 squared plus M2 R1 squared. Okay. And so once I found that, it's just a matter now of plugging that into this expression since this is 0. The whole thing is rotating this way, which is in the clockwise direction. So omega is omega in the minus z hat, if I'm taking out the magnitude right there. And I'll have minus R2 M1V z hat equals minus z hat I about the center of mass omega. And so omega is going to equal R2 M1V divided by I center of mass, that complicated expression. Whew. Okay. All right, so I'm going to come back in a little bit just to talk a little bit about gyroscopes. Super interesting stuff. But otherwise, that was angular momentum. So I'll probably spend just a little bit talking about gyroscopes in a follow-up video, 15 minutes maybe. Okay.